Discussing a little bit further on ceramics. So as we've seen, ceramic materials are more brittle than metals. And so far we've been dealing with the data had we had the chance to have it. So we've seen brittle materials perhaps characterized as not being very ductile. So the percent elongation at failure would be less than 0.5% elongation. In certain circumstances, it becomes impossible to actually test such a specimen and test in tension. You can't grip the ceramic hard enough before it fails. So just the act of trying to mount it in a test fixture for tensional work would fail the specimen at the grip points rather than at the gauge portion where it narrows. So in other words, even if you had a test specimen that was ceramic and looked like this, as you grip on up at the top and up at the bottom, the teeth of your grips may actually cause failure down at the grip portion rather than in the gauge portion here. And so an addition or another approach to doing the test work can be done. And so we'll touch on that in a moment. So in just further elaborating on ceramics, we don't have the ability to slip atoms past each other as easily anymore because ceramics, of course, involve the matter that involves cations and anions that result from metals and nonmetals having combined. And so deformation here is going to rely on dislocation motion again. And for highly ionic materials, like we've just alluded to, with a lot of charge on the two ions, so for example, like magnesium 2+ and oxide, so magnesium oxide, very highly charged species in this ceramic material. This is going to be very difficult because asking planes of magnesium to move past other planes of magnesium on their way to finding a neighboring oxide for their new position puts cations next to cations. And so this becomes difficult. So there's resistance to motion of these ions due to the charge. Okay. So on the note of testing ceramics, we can actually do flexural test work. So a specimen like a long bar that is in rod format with a circular cross section, or a square or rectangular cross section can be tested instead. And so here in cross section, we see that a point is applied to the middle of the bar, and there are two stationary points where the other ends of the bar are resting, and we ask the test specimen here to undergo a flexing as we apply force at the midpoint. Okay, so this 3-point bend test relies on 2 points being stationary at either end and a midpoint undergoing the load via the force at that third middle point. So under this condition, you might expect a bowing of the specimen as we see in the dark gray. We recognize that at the area that is bowing furthest away from the midpoint, so this green area, that we're getting a lot of tension there because that material is being asked to expand, to pull as we have to create new surface area. And so that's the area of maximum tension if you think about the matter at that surface. Okay, and opposite, where near the point where we are pushing, where the load is applied, we have compressive forces as we're asking material to kind of contract due to the bowing of the specimen. Okay, so regardless, we've got a force that you know is correlated to the y-axis information. Our x-axis information now is going to be a midpoint deflection. Okay, so notice that we know where the midpoint of our test specimen was without any load, and we're going to ask that to bow and move that midpoint lower and lower as we apply higher force values in this flexural test. Okay. So depending on the test specimen, a lot of specific information needs to go into our stress information. Okay, so the flexural stress value is dependent on the cross section. So if you're circular or rectangular. Okay, so you can see here that the force applied is in our numerator as we expect. The length of the test specimen is in the numerator. In our denominator, we have the information about the cross section. So we have the base dimension of the cross section. Okay, so that's B. And then the sort of height of the test specimen is going to be D. Okay, so D would be sort of over here, if you want, if this were a rectangular cross section, and B would be coming out of the page towards you for this test specimen if it was rectangular. Okay, so you see that information ends up in the denominator in this work. For a circular cross-sectional specimen, like a true rod undergoing a 3-point bend, we simply have the radius that characterizes the dimension of the material in cross-section, and so we're going to put all of that in the denominator in the form of that cubed. Of course, bring in pi, and again, put the length of the specimen in the numerator like we had before. Okay, so now we have some more geometric parameters involved in the stress portion. We didn't have all those necessarily before. Things like the length of the test specimen was not in the y-coordinate information. Okay, so that's strength. That's the y-coordinate, stress information. The x information is not relative to its original length anymore. It's simply the deflection value, delta. So these stress strain curves look like sigma versus delta, and simply we simply take the midpoint deflection value and use that as our x coordinate information. Okay. Very good. A note that I haven't specified here because we need the subscripts there. Could be used to identify, for example, cross-section or circular. So clearly under a flexural condition, sigma f would be appropriate there. Okay. So here's an example where a flexural test has been applied to bone. So this is a mouse femur, and we've done a 3-point bend test on it to try to get some characteristics for the bone. Okay, so this might be important if you're considering new composites or new plastics to replace bone. You might do some test work with mice before transitioning over to human specimen. Okay, so again, this might accommodate unusual test specimens where gripping carefully at the ends of a bone may not be possible, and so the 3-point bend test becomes a good option here. So here's displacement. Again, you see that registered now by how much vertical distance the fixture holding the midpoint has traveled. Okay, so there's our x coordinate information, and applied load is now used. So notice we just have force here. We're still getting characteristics of the stress strain curve, but because the cross section of this specimen is not exactly circular, not exactly rectangular, you can kind of leave it up to the reader to apply the mode which they might want. So the authors of this paper simply left that as load values. Some of you might be thinking that the circular cross-section might be the better model to help generate the true the stress versus strain curve for this 3-point bend, but they've chosen not to go to that extent and just simply plot the load. Again, you can see characteristics like we've seen before: maximum strength, a fracture ultimately, an elastic region to the graph, with a yield point shortly after that elastic region, and a plastic region of deformation out this way. Okay.